The question of whether the universe has stopped expanding is rooted in a long history of cosmological discoveries and is filled with current debates within the scientific community. In the 1920s, Edwin Hubble observed that galaxies were moving away from Earth in all directions, a finding that led to the formulation of the Big Bang theory. This theory proposes that the universe began as a singular, highly dense point around 13.8 billion years ago and has been expanding ever since. The rate at which this expansion occurs is known as the Hubble constant, which scientists have used as a vital measure of cosmic expansion. However, as we observe deeper into space, the accuracy of these measurements becomes a serious challenge. Determining the exact rate of cosmic expansion involves two main approaches: observing the early universe's relic radiation, known as the cosmic microwave background, and measuring the distances and speeds of galaxies closer to us. Yet these two methods yield slightly different values, creating what is known as the Hubble tension. This discrepancy suggests that either our understanding of physics is incomplete, or there may be an unknown factor influencing the cosmos's structure. The introduction of the James Webb Space Telescope, alongside the Hubble Space Telescope, brought new potential for clarity. Webb's powerful infrared capabilities allow it to observe much deeper and clearer images of space than any previous instrument. By studying specific markers like Cepheid variable stars, which pulse at predictable rates and serve as cosmic mileposts, James Webb Space Telescope has confirmed the accuracy of the Hubble telescope's previous measurements of nearby galaxies. This has reinforced the observation that the expansion rate in our local universe seems to be different from what we expect based on measurements of the early universe. Scientists like Nobel laureate Adam Rees have been at the forefront of exploring this phenomenon. Rees and his team at Johns Hopkins University work on confirming measurements of distant galaxies and supernovae, objects that help provide a framework for measuring cosmic distances. His work with the James Webb Space Telescope and Hubble has shown that while measurement errors could be ruled out, there remains a mysterious difference in expansion rates, one that suggests a fundamental gap in our understanding of how the universe behaves on a grand scale. One prominent theory in recent discussions is that the universe's expansion rate may be influenced by an unseen force or substance. This dark energy concept suggests a form of energy that permeates all of space, driving the universe's expansion at accelerating rates. Yet if dark energy is indeed responsible, it raises even more questions. Why would it lead to differing expansion rates at various points in time? Are there factors about dark energy's behavior we have yet to discover? The James Webb Space Telescope observations, which corroborate Hubble's measurements and highlight these discrepancies, imply that cosmic expansion is more nuanced than once thought. As Webb and Hubble work together, their combined data challenges earlier assumptions, even hinting that expansion could slow in some regions while accelerating in others. This inconsistency doesn't mean the universe has stopped expanding entirely, but it does suggest that the expansion may not be as uniform as once believed. Future missions, like the upcoming Nancy Grace Roman Space Telescope, are expected to provide even more detailed insights into the mechanics of cosmic expansion. Equipped with wide-field infrared capabilities, the Roman telescope will help scientists map the universe on a grand scale, potentially revealing more about dark energy's influence and the true nature of the Hubble tension. These discoveries could lead to groundbreaking shifts in how we model the cosmos and might unveil aspects of physics previously unknown. European and American scientists are particularly excited about the potential of the Roman telescope to examine the universe's cosmic distance ladder, the set of methods astronomers use to calculate vast distances in space. Each rung of this ladder relies on different objects, from Cepheid variables to supernovae, each observable at increasingly vast distances. The reliability of each rung is crucial, as uncertainties in one part of the ladder can affect calculations all the way up. Using Webb, scientists have attempted to ensure that any errors in Hubble's observations are minimized. Now, with more precise instruments and methods available, new observatories can further validate or challenge these findings. In the context of cosmic time, the James Webb Space Telescope has provided what some researchers describe as a cross-check on the Hubble telescope's legacy. Its observations have spanned the full range of measurements made by Hubble, showing that the Hubble telescope was correct in its findings, reinforcing the reality of the Hubble tension. Yet, the persistence of this tension hints that there may be unknown physical forces at work. possibly necessitating an entirely new model of cosmic expansion. Some theoretical physicists have posited that the universe could even be entering a second phase of expansion, where unknown factors, possibly tied to dark energy, begin to alter the speed or nature of cosmic growth. This theory doesn't suggest that expansion has stopped, but that it may be following a dynamic that fluctuates across different cosmic epochs. Such an idea would align with the observed variance in expansion rates, which seem to differ between the early and present-day universe. As scientific teams around the world analyze Webb's findings, the data could redefine our understanding of space-time. The James Webb Space Telescope capacity to observe faint, faraway galaxies opens up new possibilities for understanding cosmic history, potentially revealing patterns in the universe's expansion that previous telescopes could not detect. Astronomers hope these insights might eventually resolve the Hubble tension and reveal a unified theory of expansion rates across time and space. The findings from the Webb and Hubble telescopes' collaboration have established that the early and present-day expansion rates do not match up easily. Scientists continue to explore whether dark energy is acting differently at various points in cosmic history, with Webb's infrared precision allowing astronomers to see through space dust, revealing hidden stars and objects critical to cosmic measurements. This capability adds a new level of accuracy to measuring cosmic distances, and scientists believe it could illuminate the universe's past in ways we have yet to fully grasp. By examining galaxies and cosmic structures over vast distances, Webb offers a glimpse into epochs only shortly after the Big Bang. This time machine view into the universe's infancy reveals galaxies and star formations that provide clues to the universe's structural evolution. Understanding these early structures could explain how and why expansion rates vary, offering potential solutions to the Hubble tension. Yet, these solutions will likely take years to confirm. The data obtained so far represent only the beginning of what will likely be a long, complex journey toward understanding cosmic expansion's ultimate nature. It's a journey that could eventually reveal an entirely new aspect of physics, reshaping how humanity perceives the universe and its origins. As the James Webb Space Telescope continues its mission, researchers around the world are poring over the data, looking for patterns or anomalies that might provide answers. These observations are highly anticipated and may lead to insights into not just the universe's expansion but the forces shaping it, providing an ever clearer picture of the cosmos.